Hey everyone! I wanted to make a new video of some of the workbook problems today. I wanted to go through some of them with you, but as stated, if you saw the last video, I'm assigning all of section 9.1 except for number 8. And I wanted to go through some of them with you. I'm not going to do all of it, but just to give you an idea of what they're asking. So we'll start with section 9.1, problem number 1. So this first exercise is just deciding whether or not these statements are biased or not. And if we need later on to use the random number table, it's on a couple pages down, and part of the z-score table is on page 146 as well. So I want to just start off by saying if these are biased or unbiased. I'm not going to do all of question 1 because I think once I start it, you guys can get the gist. But question 1A, do you think a person who doesn't vote is irresponsible? Is this a leading question? Is this biased or is this completely unbiased? I think since they're saying irresponsible, they're leading towards that conclusion. So this is definitely a biased response. Do you agree or disagree with the fact that eating in class is not permitted? This sounds like they're stating a fact. They're just saying, is it true or is it false that eating in class is not permitted? So this is pretty straightforward. I would say this is unbiased. Don't you think Mr. Menschel should let us use calculators more often? This definitely is a biased question. Don't you think, even though they're saying don't you think, they're also, leading us to let us use calculators more often. Just the wording of that just is a very leading question. So I would like you to try and figure out D, E, and F. Are they biased or unbiased based on what we've talked about in class? I'm going to move on to question number 2. Sorry for all of the alarms. A cosmetics company is deciding whether or not to modify a lipstick product they manufacture. They need to do some research. They want to test if women react differently to medicated lipsticks. They randomly select 500 women and randomly assign them to 2 different groups. Sounds like it's a good experiment so far. One uses the medicated lipstick and one uses the non-medicated lipstick. Okay, sounds like we have a control group. Sounds like we have an experimental group. That all of this sounds great so far. So the question is this an example of an observational study or an experimental study? And just based off of this, right, my overall question is saying, is this an example of an observational or experimental, right? Observational versus experimental. And so really those are my 2 options. So I think it's an observational study. We're just observing what happens, or are we performing some sort of experiment? I would, certainly say that this is an experimental study because they have a control group. Control versus the experimental group, right? They have the regular lipsticks and then they have the medicated lipsticks. And so that is a key idea that this is going to be an experimental study. They're not just simply observing and seeing what's happened. That would be an observational study. Okay. Question number 3. A music school needs to test some new music stand designs and they need to select 100 students randomly from 719. Okay. So if they're going to use a random number table, how many digits will they need to use to represent the students? So we kind of started talking about this yesterday and the day before when we were looking at using a random number generator. And that's obviously going to give different results for every single person. For our purposes, for statistics, to make sure we're all on the same page, we're going to use a random number table instead to make sure that we kind of retain some control. But we know that they want to ask 100 people randomly. So we're going to select 100 students randomly from the total of 719. But they're selecting 100 from 719. 719 is 3 digits. So is 100, but like it's really the population is what's the most important. So if we're going to use a random number table, we need the same amount of digits as our population. So 3 digits is question A. Then question B says, all right, let's use the random number table. We need 3 digits, and we're going to start on line 10. What are the numbers of the first 5 students who will be selected? Remember, normally we would select 100. That is going to be a lot of work. So we're just going to pick 5 using the random number table. And it tells us specifically to start on line 10. So let's go down to the random number generator, or the random number table. We're going to start on line 10, and we're going to look for 3-digit numbers that are less than 719, right? So we need 3-digit numbers that are less than, I'm just writing this here, 719, because that's my population. If it's over 719, then we don't even have that many students. That would not be a number that we would want. So we're going to go find our number table, line 10, 3 digits, less than 719. You guys flip your page. Here's our random number table. We're going to go to line 10. So we're going to start here. And remember, we want 3 digits less than. So I'm going to write myself, I need 3 digits less than or equal to 719. That's just my own little notes. So we'll start here on line 10, 946. That's bigger than 719, not going to use it. Our next one, and we want 5 of these, right? So our first one would be 069. That's less than 719, sounds good. 788, that's less, no, actually, that's bigger than 719. 252, that's less than 719, so we could use that. The next 3 digits is 960. That's too large. The next digit is 146. That would work. The next one is 056. If I put that together, 056, that goes together, right? 056, that is definitely going to be less than 719. And now I just need one more, 695, I think is what that says. And you would continue doing this until you got 100, right? If we were using a random number table. They just wanted 5 of them. So these are the 5 numbers. The 5 numbers that are 3 digits long, that are less than or equal to 719. And we got them. We would ask whoever is number 69, number 252, number 146, number 56, and number 695 to participate in our study. So 069, 252. Yeah, I wanted the first 5. 146, 56. And the last one was 695. Sorry for the scrolling. Okay, so now you kind of have an idea. When you see another problem that asks you to use the random number table, you have to look at the population for the digits, and then it will tell you exactly where to start on the random number table and how many they want you to find, and you'll be able to come up with them. So question number 4 is very similar. It says a random group of 90 students or 90 gas stations from 121,000 gas stations in the United States is to be taken using a random number table. Okay, so you can answer question A. How many digits will be needed to assign each gas station? You can answer that question surely. Question B, would it be possible for the random sample of 90 gas stations to contain only California gas stations? Is that a possibility? And yeah, when you think about it, like it could. Is it likely? Probably not. But could it happen? Yeah, definitely. It certainly could. So we would say that these are kind of like in the land of like, is it possible? Yeah, it's definitely possible, right? Question C, would it be probable for the random sample of the 90 gas stations to all be from California, right? If they're picking 90 out of 121,000 all across the United States. Like, yes, it could only contain California, but is it going to be? Not likely. So no, we're going to say no here. Okay. So differences between possible and probable. Okay. Now question D says, would it be possible for the random sample of the gas stations to all be the exact same brand? We're talking like Shell, Chevron. When you go to different states, there's so many different other gas stations. Like, I know they have like Buc-ee's and stuff in Texas. So like, is it possible that when we're collecting this random 90 sample from 121,000 that it could all be just Shell gas stations? Like, yes, but is it probable that they'll all be the same? No, not likely, just because there's so many different ones. Now, if they were saying a specific region, possibly, but it's not looking like it. And I know I said you guys can do it, but when it says how many digits will be needed, you have to look here. How many digits is there? 6. That's your population. Okay. Question number 5 is something that you can do on your own. Again, because at the end of it, it's saying, is this an example of observational study or experiment? So question number 5 is similar to question 2. So I'm going to leave this one to you, but I'll give you a note that it's similar thought process to number 2. Okay, so I'm not going to do that one for you. Question number 6, I'll walk you through it. The Plastics company wants to test if new cell phone screen protectors are more resistant to scratches for longer periods of time in comparison to the current one we have. Okay, so they're going to test 100 old ones and 100 new ones. This sounds really good to start, like old versus new. We're going to have to set up a control group. We're going to have our experimental group, right? So we want to create a completely randomized design. So we'll have to, like, in our randomization, so we'll make it randomly select 100 old versus 100 new, right? Make sure it's randomly selecting those things. Then we would have to, like, test it out, right? Try them out, same thing, the old and the new. And then we'd have to, like, analyze the scratches. Look at, like, how many scratches do the old covers have? How many scratches do the new ones have? After, of course, this is just like normal use, nothing super extreme. Or I guess it could be, but however you're testing them, it needs to be consistent for the old covers and the new covers. You can't treat the old covers in extreme scenarios and then the new covers like you're scratching it with a feather, right? That wouldn't be fair. So if we're making it completely perfect randomized design, whatever we do to the old, we have to do to the new so that we can compare and analyze the information. And once we do that, then we'll compare our findings and decide. Like, are there less scratches on the newer ones than there are the older ones when they're the exact same things happening to both types, right? And then even further, can't just go on a notion. You could use statistics to verify your hypothesis testing here. So that's what we got. And so now we have some information in part B. The life of the old protector is normally distributed with a mean of 42 months and a standard deviation of 3 months. The average life of the new protector, excuse me, the new protector is 52 months, also with a standard deviation of 2 months. So now we have to determine if the new protector is superior, right? Like, we did the experiment, we tested old and new, we analyzed, now we're starting to compare our findings and actually decide if the new protector is better or not. right? So we have the life of this old protector has a mean of 42 and a standard deviation of 3. I'm a visual person, so I'm going to kind of like put this out here. My mean is 42. My standard deviation is 3. So 42 plus 3, this one is 45. 45 plus 3, this one is, sorry, I don't know why my iPad keeps moving. 48. 48 plus 3 is 51. And then I could subtract them on the other side. 42 minus 3 is 39. 39 minus 3, 36. 30, this is a really bad 6. 36 minus 3 is 33, right? So that's my old findings. My new findings, I don't have an X value, so I can't really compare my data values. So I'm just going to use my picture. My X, it says, oh, the average is 52 months, right? So that's going to go in the middle. And my standard deviation here is 2. So I'll have boom, 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 3 to the right, 3 to the left. 52 minus 2 is 50. 50 minus 2 is 48. 48 minus 2 is 46. To the right of the mean, 52 plus 2 is 54. And then 56 and 58, right? So visually we can tell, even though we don't have a data value X to like plug into a Z-score and see, when I'm comparing, right? When I'm comparing and looking at these things, my mean of my new one is 52. 52 is already bigger than 3 standard deviations of the mean to the right. And remember, like, this is taking it way back, right? 100% of our data is under this curve, right? And to the right, like 52 is to the right of 51. We also know that this little tail right here is 0.15% from the empirical rule. So you're telling me that the average life of the new one is way better than the old one, right? There's under a 1% chance, like 0.15% chance that the old protector would last as long, right? Like, yeah, this is definitely a lot better, right? Like the average of the new is more than 3 standard deviations above the mean. That means, like, really, like, since it's above, that's 100 minus 0.15. That's 99 point, oh my gosh, literally so small. 99, let me punch this into my calculator. 100 minus 0.15, 99.85% more effective. And that's just me saying, like, oh, I don't know exactly where 52 is on there. It's just over here. I know it's over here, right? I guess I could have plugged in 52 minus 51 over 3 and then did 100 minus that. But, like, just looking at it visually, yes, this is new superior. It was much more superior. The mean is a lot higher than the old, so it's going to last quite longer. Now, Part C is giving us some actual details. It says if the new protector from Part B had an average life of 43 months, will we believe it's superior, right? So instead of this, what we have here, right, I'm just going to erase the bottom part, leave everything else, or not. Now it's saying in Part C, if the average life was 43, so I'll put it right here, 43 instead, and let's say that it still has our standard deviation of 2 months. So it would be 45, 47, 49, over here, 41, 40, 39, and then one more, 38, 37. So we have our picture here. Now, is it more superior? So again, let's kind of compare, right? If the average is 43, that's only a little bit larger than the average that it was, right? So no, I don't even, like, I guess I could do this statistics here, but like it's not by much, because 43 is only slightly larger than the old average, right? Like the average's life is slightly longer, not a significant amount. You want a significant amount to be able to tell if your experiment is going to work or not. Okay. Number 7, Forever Tread Tire Company manufactures bike tires. They've developed a new type of tire, and they want to test 200 randomly, and they have 8,476 customers. So I'm going to leave number 7A to you to use the table, right? Use the table to determine what will the numbers of the first 3 customers selected. But I want to answer part B, so I think it makes sense. Why will matched pairs design be better than a completely randomized design for tires, right? Forever Tire Tread Company. They want to test these tires for bikes, right? It's specifically for bicycles. How many wheels do bicycles have? Well, they have 2 wheels. So matched pairs, because there's 2 wheels on a bike, yeah, that would make more sense, right? 2 wheels on a bike, so matching would be better, right? If this was just talking about tires on a vehicle or something like that, or any other scenario, right? Like maybe having 2 of a kind, 2 matching pairs, and then comparing those is going to be better in comparison to just picking something randomly. Or if it was a unicycle, then you only need 1, and it can be totally randomized design. But instead of just picking 2 random ones, we want to make sure we're picking 2 of the same, 2 matched pairs, because there's 2 wheels on a bike. Again, remember, we're not doing number 8, so you can just cross it off. It's actually very similar to the tree farm problem we worked on earlier. And then question number 9 says, the PowerSure battery company designed a new type of long-lasting battery, and they're testing it. They're going to pick 80 batteries from 900 to see if it will last as many hours. If they start the batteries from 001 to 900 in the random number table, what are the numbers of the first 5 that will be detected? I'll leave this to you to use the table. I'm not going to do that. If the lifetime of new batteries in a flashlight is normally distributed with a mean of 110 hours and a standard deviation of 10, and they guarantee that their batteries are going to last 100 hours, what % of batteries will not meet that standard? So let's think about this for a second. This is definitely going to result in Z-score. So let's set up the information that we know. I'll help set you up, and then you can finish it, okay? So we know that it's normally distributed with a mean of 110 hours. So let's write out what we know. Mu is 110. We also know the standard deviation is 10. So we have standard deviation is 10. And they guarantee that their batteries are going to last at least 100 hours, right? And this is all about hours. So X is going to be 100. I'm going to put plus to remind myself that it's bigger than 100, right? Maybe I won't, but like this is like an above problem. It's higher than 100 hours. So we want to figure out what % is not going to meet that standard. Let's set up our Z-score. X minus mu over sigma. We have X, that's 100. We have our standard, or our mu, we have our mean, 110. And we have our standard deviation. This is going to give us, excuse me, 100 minus 110 all over 10. That's like negative 10 over 10. This is exactly 1.0, right? So my Z-score is 1.0. if I go to the z-score chart, right, down here, 1.0, here's 1.00, I get 0.8413. 0.8413 from the chart, right? That's the area that all of, like, let me just draw a picture to help this make sense. We have our mean is 110. We're saying that we have 3 to the right, 3 to the left. This is going to be 120, 130, 140, 100, 90, 80, and we're saying specifically that we're right here at 100, right? We're right here, and we're guaranteeing that our battery is going to be over 100 hours. So we're saying that our battery is going to be over here, guaranteeing all of this information over here. So when I go to the z-score chart, this would be negative 1.0. Do I have negatives in this chart? Okay, I'm looking at the wrong one. You guys have it on our Canvas page, the z-score chart. I want negative 1.0, not positive 1.0. I guess if I subtract anyway, it will probably end up being similar, but I'm just going to go to our z-score chart. That's to be consistent with the understanding here. So when z is negative 1.0, so silly. If we go into our chart, negative 1.0, when it loads, negative 1.0, okay, here we are. We would get 0.1578. Right? That's from the chart, which is going to be 15.78. And remember, when you read when you're reading the chart, just like I am here, it's always the value to the left, right, of whatever your z happens to be. So here, I'm saying all of this stuff right here, that is 15.78%. And what it's asking is what percent of batteries are not going to meet that standard. I'm specifically talking about all the batteries that are not going to last over 100 hours. All of this, what percentage is that? That's our 15.78. That's where we're getting that. So I guess I walked you through all of this problem. Anyway, finish up the rest of them and submit them on Canvas. And don't forget your Desmos link for this assignment. I hope this was helpful.